We're going to talk about irrational numbers, and then we'll talk about infinities involving irrational numbers, and we'll be good. Let's see. First of all, I'm going to tell, well, a story. This is a story, but it's sort of kind of true. But you know how stories get when they happened a very long time ago? And a little tall. There's a little bit of tall tale in this, but it is based on a true story. So a long time ago, there was this kind of crazy group of people, the Pythagoreans. They were kind of a cult. Just a bit.
What's a cult?
They're a group that had interesting religious beliefs, very strong religious beliefs. But they were, they believed that the entire universe could be thought of in terms of rational numbers. So the reason they thought this was actually a really interesting thing. So if you take a musical instrument and you, like a violin, and you pin it down exactly halfway and you pluck that, it makes a tone which is one octave higher. And if you split up that string into other fractions, you get nice harmonies, perfect thirds and fifths. And they noticed this, and they decided that this is the way the entire universe works. Everything in the world is beautiful harmony. And if only you could attune your mind to the cosmos, you could hear the beautiful music that the planets in the sky are making as they go around the Earth, which we all know is true. All the planets go around the Earth. And you could just hear them. And of course, they had to be in orbits which were perfect rational numbers of each other.
And perfect circles.
Perfect circles, of course, perfect circles. Don't be silly.
All on the same planet.
All around the Earth. And if you just, and the reason you don't hear it, that this beautiful music of the spheres, the harmony of the spheres, is because you've been hearing it all your life. And if you could just purify your soul enough, you could hear it.
I'm detecting
So they
Zen.
avoided eating beans, and they did all kinds of other stuff. And
What's the matter with beans?
don't know, but apparently beans were bad. And they did all kinds of things, and if you followed enough of the rules, you would get to be pure enough to do this. But there was a problem.
What?
One day, one of the Pythagoreans thought about the Pythagorean theorem.
Oh, I know that.
You know that? What is the Pythagorean
I
theorem?
know what it is.
What is it?
It's like a square.
Yes.
And you're trying to find a square inside that square that's half the size. And this is how you find it. I've looked.
Oh, that's, yeah.
And they say that the formula to do it is like, let's say this whole thing is 2 and that's 2. You do like,
So wait a minute, is that half the size?
yes.
Why is that square half the size of the whole square?
I'll show you.
Yeah, Grace?
Grace squared. It's, wait. Can I come up with that?
Yeah. Can you explain to me why that's,
If you divide it into even fourths,
yes?
these parts are half of each of their fourths. So,
Half of that. Okay. Is she right?
yeah.
Okay. Carry on, Reza.
So like, let me change this to 1. Like,
So you're
it's like
changing,
the
this is
first-
1 right here?
Yeah, the whole thing's 1,
Okay, that's 1.
and that's 1.
I didn't do a very nice brace.
So the way to calculate it is do 1
Yeah.
plus 1 is 2, and then do the square root of 1 plus 1. 1 plus 1 is 2, so the square root of 2 is like how far from here to here.
Oh, from here to here?
Yeah.
Right over on this, like on this one, right?
Yeah, right.
So let's back up, actually, a little bit. Suppose you had a triangle, and it was a right triangle, and this side was 3, and this side was 4. How do you figure out the length of this side?
A squared plus B squared equals C squared. So 3
Let me
squared.
write this
4
lower.
squared.
A squared plus
Square
B
root of
squared equals C squared. In other words, let me change this a little bit. A squared is actually 3 squared in this case, maybe.
3 squared is 9.
Here's the square, yes?
What?
This is 3 squared. Why is it 3 squared? What does that mean? Why do I say this is 3 squared?
Because it's just.
Aiden? Why is this 3 squared? What's 3 squared about this?
That's a square.
It is a square, and why is it 3 squared?
Maybe what? Because that's what the Pythagorean.
What is 3 squared?
Oh, b times 3.
Which is?
9.
And what do I have 9 of here?
It's not.
Do you know what I have 9 of, Asian?
I know.
What do I have 9 of? Mama?
Square units.
I have 9 square units. Let me draw them more carefully. So, if this was 3, it means that I have 1, 2, 3, right? And 1, 2, 3. And if I, what do I have 9 of here? 9 square units. So the area of that squared is 9, or 3 squared. Okay? Now let's do the same thing over here. I'm going to build a square on this side, and it's
16.
16, 4 squared. All right. Yes?
So you add them and you get 25, and then you do the square root of 25 to get.
Do you get
that
one?
one.
You get
5.
25?
No,
Well, let's see. Let's do it more slowly. What is 3 squared again?
9.
9.
And 4 squared is?
16.
And 9 plus 16 is?
25. Square root of 25
Is C squared. So C must have had to be
5.
5 as long as it's a positive length, which, well, it looks pretty positive on here. So let's see. Here it is. 5. So 3 squared plus 4 squared equals 5 squared. In other words, the Pythagorean theorem says that the square built on one of the legs, the area of that square, plus the area of the square built on the other leg equals the area of the square built on the third leg. That's what that thing says, right?
As long as the third leg is the longest leg.
Yeah, you have to make sure that that is the hypotenuse, right?
Meaning it has to be 1.
What if I took, instead of squares on the legs, what if I took semicircles? The semicircle on that leg plus semicircle on that leg.
Oh, I know what it is.
This area plus this area?
I know.
What?
Like, if you're trying to find out the area,
Mhm.
like the area of a circle would be
Okay, good.
radius to the second times pi. So you would just do radius to the second times pi divided by 2 since it's half.
Good, so let's do that. What's the radius of this?
A.
The radius?
No, it's
Half of
A.
A.
Yeah, half of A, right? Because the diameter is A. Does everyone agree?
Yes.
So we take the radius, okay, and what do we have to do to find the area of that circle?
Oh, you do like A to divide by half to the second power,
Okay, so the second power, because this is the radius
and
squared,
then you do times pi.
times pi.
First you do.
So this is
to
the area of
second-
that. Well, that's if it was a full circle though, right?
Mhm, yeah, and then you divide it by 2.
Okay. Is everyone good with this? The
Yeah.
pi- That's divided by 2 because it's a semicircle.
Yeah.
That's pi, that's the radius squared. Everyone good?
Yeah.
Okay, let's check the area of this one. How do I find the area of this one?
Half B. Well,
Half B.
I times half B.
It's going to be real similar, right?
Yeah.
Okay, let's see what this works out to. What do I get if I do algebra at this?
You have to like transfer it to numbers.
Nah, algebra.
Yeah.
Algebra. So what is this? If you have a over 2 squared, what is that?
That's 1/2 a squared.
Yeah, what is a over 2 times a over 2?
Over
A.
2.
Well, it's times though.
Oh, I know what it is.
A over
A
2.
over 4.
I know what
A over 4.
it is.
A over 4.
I know what it is.
Yeah, A over.
Is
No,
I know
A
what
squared
it
over
is.
A
4.
squared over 4, right?
I know.
Okay.
It's a squared over 4.
So you agree with that? That's a squared over 4? Okay, so let's do this. Pi over 2 times a squared over 4. Let's keep going. I think we can do a little bit more combining here. You guys see the pi over 8
Yeah.
here? I can multiply these two together.
Yeah.
Yeah? So I'm going to get pi over 8. I'm going to put the a squared down on the ground. Plus pi over 8 b squared.
That is the
And now I'm going to factor out the pi over 8.
Pi over 8 is like 0.39269.
What do I get when I factor it out? What's left behind?
A squared plus B squared.
Because the distributive property would put both of those back again, put that back in on both
It
pieces
does.
again,
Look.
right?
Doesn't that look familiar? A squared plus B
And
squared.
a squared plus b squared, we know what that is according to the Pythagorean theorem. In this right triangle, it's got to be c squared. So this is equal to pi over 8c squared. And guess what? Pi over 8c squared is the area of this. Right? So, it works for semicircles too, and actually it's even crazier than that. Pythagorean theorem, you could have a weirdo squiggle on this one, and as long as it's similar, you could have weirdo squiggle scaled up here, and you could have weirdo squiggle on the hypotenuse. As long as that's a right angle, and that's A and that's B and that's C, the area of the weirdo squiggle on A plus the weirdo squiggle on B, the area of that, is equal to the area of the weirdo squiggle on C. It doesn't have to be a square. That's the thing that's nutty about this. Pythagorean theorem holds for any shape.
Weird
But-
squiggles are ugly.
You don't like my weirdo squiggles?
They look like mittens.
They do kind of look like mittens.
With very sharp films.
But the thing that you have to have there,
Mittens for
it has to be scaled up though, or else it wouldn't work. Okay, let's
Like mittens for people.
let's come back to this one though.
And one won't have to.
So- One day, there was this guy who was Pythagorean, and he started thinking about this length right here. Now, according to the Pythagoreans, all the numbers in the entire world were rational. They were rational. They were all fractions, like 3 out of 5, 3 over 5. That's a nice fraction. They were all fractions. Everything was about ratios. But one day, one of the Pythagoreans thought about this number, and he realized it could not be a fraction. What?
I know why it's not a fraction.
Why?
Because the square root of 2 keeps on going forever. That completely exits it, gets it out of the fraction family because the number keeps on going. You can't like say, this is the end of the number because it keeps on going. The square root of 2 goes on and on forever.
Okay, let's start with the 7th. This means 1 divided by 7, right? Let's do it. Are there any 7s in a dollar? Can I take a dollar, a bill, and split it up nicely?
No.
No, but if I turn it into 10 cents, can I start splitting it among 7 people?
Yeah.
Yes? How much will it, or I should, so if I split that into dimes, I should say. So how many dimes will each person get if I took a dollar and cashed it in? They'd all each get 1. 1 times 7 is 7, so I've given out 7 dimes. And how many dimes are left?
3.
3 dimes are left. But now I can take those 3 dimes and cash them in for pennies. And how many pennies will I get? 30 pennies. So now I'm down to 30 pennies. And if I take those 30 pennies and pass them out among 7 people, how many will they each get? How many will they each get? 30 divided among 7? 4. And 4 times 7 is?
20.
And so that means I gave out all but 2 of them. And now I have to have a coin smaller than pennies, so I slice and
You could
dice.
use mills.
Mils, sure.
What's a mill?
What a mill. We learned.
Tenth of a penny, I guess.
Yeah, we learned about it in math one day for some odd reason.
How many sevens?
That seems to be more history.
How many sevens in 20?
2.
2. And we go 2 times 7 and it is
14.
14.
I know what you.
6, hold that thought.
Ah.
And we how many sevens in 60?
8.
8. 8 times 7 is,
I know.
and we subtract and we get,
You've gone past mills now.
oh yeah, we're way past mils.
5.
And now what?
I have a question. I
5.
have to say something.
5 times 7
35.
is 35. And then we subtract and we get
Oh my lord.
5.
5. And we bring on down. And how many sevens
Can I
in
say
50? Not yet.
7.
7.
Oh my lord.
And then we take 7 times 7 and it's 49. And then we subtract and we get 1. And we drop the 0 and we get
It
what?
is a fraction.
4.
It is a fraction.
What is next?
1.
1. And 1 times 7 is?
It repeats.
And we're back into the repeating pattern. Is everyone with me?
Yeah,
On
it
that?
is a fraction. It repeats.
It repeats. So this answer here is 0.142857 with a bar on it. Yes, sir.
Because it rounds. It rounds. And it rounds. That they found out that you would like. What I found out is like if you divide 1 by 7, that you get like 1.42857, and it would keep on repeating.
Yes.
Forever and forever. You would always have 1 left over, no matter what you do.
Actually, I totally messed that up, so I just erased it. But what's 2 sevens?
I know.
Do you know, Aiden? What does it start with? Point what?
I know what it starts with.
Aiden, do you know?
0.28.
28.
5714.
5714. Yes, indeed. And it repeats. Why does that happen?
I know why.
Why?
Because if you have that 1 left over,
Yes.
and you make your 10,
Yes.
you keep going in the same process, because 10 divided by 7, if you like, let's say there are like, you have 7 friends,
Yeah.
and you give them each one cookie. You have 6 friends and you each give them 1 cookie, plus you get 1 cookie yourself, and you have 10. You would have 3 left over, and you keep working up until you get 1 left over, but that one stays on forever. You can't get rid of that one.
No, I get that cookie. That's the thing on here.
I throw away all my cookies. I want to diet, no cookies.
All right. Here's what happens. Let's look at these remainders. When you take when there's a 2 left over here, a 0 gets filled in, right? And what happens? What's the next remainder down after the 2? What was the next remainder we had? 6. And then what was the next remainder after that?
4.
And then what was the next remainder after that? 5. Then what? 1. Then what? 3. And then here, what's the remainder? 2. And so here what we'd have to do is fill it in with 0. It's the same remainder as what we started with, right? So it's going to behave the same way. Now, do we have a remainder of 1 somewhere here?
Yes.
How about 2?
Yeah.
3?
Yeah.
4?
5, 6.
5? 6? Why not a 7? Why didn't I ever get a remainder of 7?
Even.
Right, if I got a remainder of 7, I should have stopped, right? What about 8? Why did I never get a remainder of 8?
Because you would have been able to do 1 more group of 7 and whatever you were.
I should have gone bigger, right? If I had a remainder of 8, I messed up.
Yeah.
Right. So the only possible remainders for sevenths are, well, 1, 2, 3, 4, 5, 6. In principle, 0. It would stop then, right? So 7 sevenths would have a remainder of 0 and we'd be done. But what's interesting is if you draw sort of the cycle of possible remainders like this, 1, 2, 3, 4, 5, 6. Remainder 0, remainder 1, remainder 2, remainder 3, 4, 5, 6. What we find out for sevenths is that a remainder of 2 leads to a remainder of 6, which leads to a remainder of 4, which leads to a remainder of 5, which leads to a 1, 3, and then 2. Now 0 kind of just leads to a remainder of 0. If you did 7 divided by 7, you'd get a remainder of 0. If you went again, you'd get a remainder of 0 and 0 and 0. So you get this pattern of remainders. Yeah?
Where's
Could you
3 digits?
continue, showing what it ends up to?
What do you mean?
Just keep
Could you
going.
continue, drawing out for what it ends up to?
So you would
Drawing
do
this one?
2, 6.
Yeah, because once you get back to the beginning, 1, 3, 2, 6, 4, 5, these are the remainders, not the digits, right?
It starts with 2. And keep going all over again?
So the digits, the remainders start cycling, and so the digits that go with the remainders start cycling. Yeah?
But if you have 3.5 sevens, you get 0.5.
That is very true. So, sometimes they quit early, right?
Yeah. If it's a nice fraction, it's like 3/5 or a 10.
Let's look at this one, 3 sevenths. What is it going to be? What's it going to start with? Point what?
4.
4. And then what?
2.
2. And then what? What comes after 2's?
8, 5, 7,
5,
1.
7,
1.
1. Yeah?
So it's
And repeats. And what about 4 sevenths?
8,
Well, this is a little bit more than a half, right?
1,
So it's going to start with point what?
5,
5, a little bit more than a half. Then what?
7,
7,
1,
4, 2, 8. 5 sevenths. What will that one be?
5,
6.
6,
There's no 6. It will be the 7.
There's no 6. What's in no 6?
There just isn't.
7.
6 sevenths will end up starting with the
1.
8.
No.
5, 7, 1, 4, 2. Sure enough.
Cool.
So here's the thing. This, in a way, this sort of proves why rational numbers always have decimal forms that, what?
Don't repeat.
That
Go on forever.
do repeat or stop, terminate.
Like we stop.
Like a half. A half is what? What's the decimal form of a half? 0.5, technically 0.0000, but 0.5, right? It stops, or we call that stopping.
Yeah.
So it either terminates or the rational numbers have decimal forms which repeat. And can they ever just keep going on and on and on and doing different and different things?
That would be irrational.
That's right, but they can't, because how many different remainders can a rational number have? It can't have more remainders than one less than itself, right?
Yeah.
What about pi?
Well, we're talking about whole numbers. Okay, so the denominator of the fraction. So if I give you 1 over 47, this will have, it might have a decimal form that might repeat. What's the longest it can go? Yeah?
You can go on for
46
infinite.
numbers, and then it will repeat.
It can go at most 46 numbers, and then it must repeat. It might repeat sooner, because some numbers do. 13 is a number that doesn't use up all 12 of its possible digits. So sometimes it doesn't use up everything it could. It splits into cycles. So let's look at that. I think let's try to find out what 1/47 is. So, does everyone have a calculator?
I have a calculator.
I have some cheapo calculators. Let me go get some. I'll be right back. What I want you to do is, somebody who has a calculator, do 1 divided by 47 and put the start of 1/47 up on the board.
How many digits?
Don't trust the last digit because you don't know whether it's
Yeah,
rounding
because
or
it's
not.
rounding.
It
It does round.
Never trust the last.
Okay, 0, 2, 1, 2. Can someone go up there and write it?
Yeah. 0.
0, 2, 1, 2.
Here, Agent, I'll
Can
tell
I
you
round
real quick,
it?
and you can just write what I tell you.
It'll probably be easier than trying to calculate it.
0, 2,
Oh, that's-
1.
Oopsie.
I lost it. It's here. I've got it.
This is fun.
0, 0.0.
Okay, fine. Still in the bed.
All right, 0, 2, 1, 2.
Point 0, 2, 1, 2.
Okay. Let's see, who needs a
Point
calculator?
0, 2, 1, 2.
Calculator.
What?
Calculator.
0,
1,
2, 1,
Screen
2.
go, Eden.
7, 6, 5.
No, that's one too many 1, 2s.
What's that? Yeah.
7, 6. No, it's
It's point 0, 2, 1, 2.
point 0, 2, 1, 2.
Joseph, lied it out.
1.
And here's what I want the rest of you to do. Pick
7,
different
6.
47ths, like, I don't know, 7 47ths or 25 47ths. Pick different 47ths and write down the decimal forms because we'll find
No,
pieces
no,
of them in this.
Agent, put 5, 7.
So pick out different 47ths and write down the decimals.
Here.
We'll just put the
5,
cap
7.
on the side then.
5, 7. No, that, your calculator
So
runs out.
find different 47ths and figure out the decimal for them and write them down. Write down the fraction and what you get.
Can you trust your last digit if it's less than 5?
No, because you don't know what the next digit off the screen did to that digit, right?
Yeah, it rounds.
If the next digit off the screen was an 8, it might have already rounded it
That's as far
up.
as the iPod's scientific calculator.
Okay, so we've got 0.0212765. Is this a 9?
Yeah, it's a 9.
9, 5, 7, 4, 4, 6, 8. So far, let's see, did anyone get another 47?
I did 2 47.
And what was that one?
Point 04255
I'm so sorry, 0.04.
255319.
Okay, now this, and you didn't give me the last digit, right?
Yeah,
Is it-
I did.
Okay, good, because I don't trust that one. But you know what we really want? I really want something that has a 0.4468 in it. I want some 47th that has got 4468 and then some other stuff. Because I would, that's enough of a pattern, I believe, that we've fallen back into it. So where would you hunt? What kind of 47th would start 0.4468 something?
Let me see.
How many 47ths would that be that would do this? Well, would it be less than halfway or more than halfway to 47?
A little bit less than half.
Less than halfway to 47.
20.
Yeah?
4, 4, 6, 8.
What did you get?
21.
21 47ths? What
Yeah,
is
me
it?
too. I got that too.
Yeah, I
did.
tried 20.
4, 4,
I
6, 8, 0, 8, 5, 1.
851.
And then I have after 5, 1, 0, 6. This is not in the 21 though. So you can.
Oh, you got that from another number?
Yeah. I
Well,
got
good.
that from.
That's all right. So let me tack it on.
24. I gotta read it.
So 0851. And which one did you get that from, Shlomo?
24, 47.
So in 24 47s, what did you get there?
5, 1 at
51
06,
06
38,
38
29,
29
78,
78
72,
72
3.
3. And do I trust the 3?
There's a 4 after the 3,
Okay.
so you can trust
I
it.
can trust the 3. Okay, just gotta check. So we got 5106 382978 723. Okay, we're not back to the beginning yet. Yes?
I did 347.
Okay, and what did you get for that one? So we've used these.
0.06. And then
Then what?
0.06 and then 3, 8, 2, 9, 7, 8.
That-
Which is
that's
interesting
part of
because that actually fits in here, doesn't it? Do you see that? So I guess we've got that one in there now. Okay, what other 47ths is? We want something that's gonna maybe start 0.82 or 8723. 0.8723.
I got one, 41/47. Immediately it starts 0.8723,
Okay,
404, 255, 319, 1.
and that's a trustworthy one. Okay, so 8723, 404, 255, 3191.
Oh, I get another one.
You got another one? What is it?
It's 2347.
Okay, what is that one?
0.489 36170, and the last number's 2, but I don't want
We don't trust that, yeah. So we got 489. Is that anywhere up here yet? Anyone see that? 489, 36170?
4, 8.
I don't see it yet, so let's save it because this might come up a little bit later. I think we want something that starts with 3191. 0.3191. Can anyone find that one? Some number of 47ths comes out 0.3191. Yeah.
Wait,
Where's the
I lost it.
Oh, never mind.
I have a 3191. It's in the middle of,
Yeah.
it doesn't start, but it's in the middle of,
Okay, I'll take it.
I have one that
forget how
starts with
many.
0.319.
Oh,
It
you
was-
do.
it was
Grace has
12.
got one.
It was
Let's let
12/47.
Grace. What was yours, Grace?
0.31, I forget what it is.
Oh, you forgot what it was. Okay, what was it?
Hold on.
Oh,
1547.
okay. And what was the answer?
0.3191 48936.
For me, 1547.
48. Did I say?
489.
Oh, I got 9.
3, 6.
3
One.
9.
No, it's the last 6.
Well,
So,
actually,
4, 8,
on the
9, 3.
iPod, I did 15 and 0.3, 3617
3617
02
02.
1, and the 3 at the end isn't
So
trustworthy.
you have a super long number of digits there. Okay, so let's keep going. So 3191 4 8
Wow.
9
Well, that 0 looks like it's starting a repeat,
6 1 7.
and the 0 looks like it's
Oh,
repeating.
0 2 1. That does look
It
an
starts
awful lot like
with-
0, 2, 1, let's do 16. No.
And notice that 04255 is in there, look.
Yeah.
And this one should be in there. Oh, look, it's right here. 489 36170, right?
I'm pretty sure.
And this is starting to repeat again.
Oh,
So let's see how many digits this is.
Wow.
1, 2, 3,
47.
4, 5, 6, 7, 8, 9, 10. I'm going to mark it. This is 10.
Yeah.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here's the next 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Next 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Next 10. 1, 2, 3, 4, 5, 6.
Oh, I was
That's
so
46.
close.
It's using all of its digits.
It is using all of its digits that are possible. It's using remainders 1 through 46, right?
Yeah.
Yeah.
Every single one of them got used before it started repeating. It couldn't have had more. Because if it ever had a remainder of 47, it would have stopped. If it had a remainder of 48, we messed up,
Yeah.
right? And if you have the same remainder at a step, it's when you drop down to 0, it's going to behave just the same every time, right? So if you get back to the same remainder, you're in a loop automatically. So you can't have a, oh no.
Okay.
All right.
Can I say something?
So yeah, go ahead, Reza.
You were talking about someone that discovered that thing.
The Pythagorean theorem thing? Yes.
Like I meant like he found out that number from
Irrational number squared
Yes.
root 2.
So can you go on with that story?
Yeah, let's go on with that story. Good call. So, rational numbers always repeat, but let's look at this. What we're going to do is we're going to prove that the square root of 2 can't be rational. It can't be a fraction.
Oh, I can prove it.
Yeah, can you prove it? How do I do it?
Well, I know part of the square root of 2. Can I say it?
Yes?
1.41, 42,
1.41, 42. Yeah, sorry.
and then 135,
Uh-huh.
and then 623.
623. And if you square that, does that make 2?
Not exactly because it keeps on going forever. So you have to
No,
also
I
put
squared
dots.
that and that. I squared that and I got 2. I squared 1.
That's
My
because it's,
calculator only
That's
shows
because it's
to
rounding.
yeah,
6 too, but I squared it and I got 2.
That's
because
because
it's
it's rounding.
rounding too.
Well, let's think about this for a second. We want two numbers that are going to square up to make 2.00000 forever, right?
Mm-hmm.
So,
I know.
well, can it end with a 3? Can it stop there?
No, it can't.
Because then 3 times 3 would give you a 9 in that ones place, right?
Yeah.
So that it can't end like that. So you're right, this thing is, it's like this, but the thing is, how do you know that it just doesn't start repeating after 1,000 places? Maybe
I know how you
this is secretly something over 1,000, or something over 1,013.
No, I know how you can prove it.
How?
Because if it repeats, it's never gonna
That
get
number
back to it.
is not
Because the number needs to keep on going forever, like so it can't ever repeat.
How do you know that it needs to keep going forever differently? Maybe it goes forever, but it repeats.
If it repeats, it's not gonna work that way because you need to get like closer to it.
What? Well, how do you know it doesn't repeat? That's the thing I don't understand. Yeah.
I squared that and got 1.9999999979326.
793256. I don't go that far.
Yeah, his calculator is kind of super
Yeah.
place
Supernatural
value.
supernatural
Got a lot of-
calculator.
That's right. Something like that.
16 digits.
It's got a good number. So this isn't enough, but you know what? I think we can get out past the point where your calculator can tell. That's the other problem, right?
Yeah. For example, if I do
Oh,
2,
maybe
even
if you want to
where
go further, I was thinking about something.
1.41421356.
I don't think so.
Yeah.
I can't find the square
If
root
you
of
do
both
the square root
numbers,
of
actually.
10, like,
Square root.
because the square root of 10 is 3 point something.
I know it's gonna be
so I was
somewhere-
thinking about
It's shift and
it
that.
being
I was
the
about to
rest
say,
of the
I know it's
pieces
some
of the square root
ridiculously
of 10.
obvious
Maybe
ways
so.
to make cylinders.
So let's go ahead and look at. I do want to show you a proof that this cannot be rational. Yes,
I can
because this
add
is
on
what
to
the
that
what the got
square root
that
of 2.
poor guy killed.
What?
Decimal.
They killed him.
It's 1.4, that ends at 62.
Wow, so cold.
Oh, you know.
7309.
The-
The Pythagoreans killed.
Killed its own member.
Yeah, they killed the member because if it got out, this proof that I'm about to show you, that the square root of 2 is actually not rational, got out. You know, or they were worried it might get out. And if it got out, then their whole basis of their ideas of how the world worked would have fallen to the ground, right? Because they believed everything was made of rational numbers
So
and
because
ratios.
they were scared to be mocked for that,
They were
killed somebody.
scared that this might not be true, and so they killed
That's
the
not
messenger.
nice to do.
It's not nice. You should go tell them. But anyway, this is.
Pat, there's still Kathy.
But here's
whatever.
here's the proof. Yeah, you ready?
You can add 7309 to the square root of 2.
I can add what?
7309.
7309.
And then there's an untrustworthy 5.
Untrustworthy 5. Okay. We don't know if that might repeat someday, but here's how we're going to prove that it doesn't. It's
Yeah.
not rational. Here's how. This is called a proof by contradiction. In a proof by contradiction, you assume the thing that you wish was true, and then you prove that it can't be true. So sorry, it couldn't have been true. So here's the proof. We say we would like the square root of 2 to actually be a rational number. So suppose the square root of 2 is actually a fraction. It's a over b, where a and b are whole whole numbers. You guys know what I mean by whole numbers?
Yeah.
Yeah.
Not fractions or decimals or anything else. And A over B is in lowest terms. You guys know what I mean by lowest terms?
Yeah, it's
Yeah.
Or
the least
simplified?
complicated.
So the thing is, every fraction, if you really can write it as a fraction, it's possible to make it be in lowest terms. So if, for example, this was 3/6, you could reduce it down, make it a half, and that's the one we want to use, okay? So if it's possible to express the square root of 2 as a fraction, it should be possible to pick the fraction that's in lowest terms already. Is everyone okay with that assumption? You sure?
Fine with me.
Are we good? Okay. Here's what we're going to do. We are going to square both sides. What do we get? What do you get when you square the square root of 2?
2.
2. That's the whole point. Square root of 2 is the number that when you square it, you get 2.
That's kind of.
It would be
So, this side is a squared over
B squared.
b squared. Now how do I get the b squared off of this side? How do I get it to the other side?
You can't.
I can. We can do something to both sides of the equation to get rid of this, b squared. What do we do?
You multiply them both by b squared.
Absolutely. Multiply this side by b squared.
3.
Multiply this side by b squared. As long as I do the same thing to both sides, I keep the equations in balance, so I haven't upset my balance.
Well, first we need to know what B squared is.
We do, but we're about to find out something about a squared, though. This tells us something about a squared. It's equal to 2 times something. What kinds of numbers are 2 times something? Think about it. 2 times a number, what do you get if you do 2 times something? Yeah,
An even number.
right. If you do 2 times 7, what do you get?
13.
Is that number even?
Yes.
If you do 2 times 101, is that result even?
Yes. 202.
If you do 2 times something, a whole number, will it always be an even result?
Yeah.
Always and always. So, this tells us, this means a squared is even. Now let's think about a. A squared was even. What kind of number could a be?
An even number.
Yeah.
Could it be odd?
Yeah.
So take an odd number. Give me any odd number.
3.
3. Square it.
9.
If you square it, you get 9. Is that even?
No.
Okay, give me another odd number.
5.
5.
Um,
You square it, you get?
25.
Is that even?
No.
Is there any odd number that when you square it, it will be even?
No.
Can we be sure?
No. I'm not sure.
Can anyone prove it? Yes?
I can.
Aiden?
Well, since an odd number can be split, it times an odd. Since an odd number can't be split in. Since an odd number can't be split in half, an odd number times an odd number. Well, the only way for that to be split in half would be for the odd number to be split in half, which is impossible.
Okay? Yeah?
But never mind.
There's also a theorem here that we're playing with called the fundamental theorem of arithmetic. And it tells us that you can make factor trees for things. Has anyone ever made a factor tree?
Yes.
No. Let's try it. 54. What could you split 54 into? Asia?
27.
And 2?
Yep.
Sure. What else?
9 and 3.
9 and 3. And then? The 9 can split
3 and 3.
3 and 3. So 54, it turned out this time
So it's made
that
up of
the
3
prime numbers, because the prime numbers can't be split other than into themselves in 1, right? So it would be silly to keep going. So it's 2 times 3 times 3 times 3.
Mhm.
Yeah, Asia.
Or you could change that to 2 times 3 to the third.
Oh, you're right. 2 times 3 to the 3rd power. But what if I had split it up differently? What if I split that into 6 times 9 at first? Then what would happen?
Well,
2 times 3.
Times
three
3
times three.
times
3
2.
times.
Do we get a
So-
different final result?
No.
The prime numbers that you break a problem up into, the factors, always are going to be the same set of prime factors. That's called the fundamental theorem of arithmetic. And what's true about even numbers in their prime factorizations? What is true about even numbers? If you have an even number, its prime factorization has to what? Yes?
Include 2.
It must include 2. So it can be split, like Aiden said. And if it doesn't have a 2 in it, what's true about it? It's odd. And so, if a squared is even, it means that a has to also be even. So this means that a is even. Now we're going to do something pretty crazy. If a is even, we can write it as 2 times something, right?
Yeah.
Mhm.
2 times b squared.
A equals 2. Well, let's not use b. Let's use a different letter. What letter would you guys like?
G.
G, where G is a whole number, right? This is going to make it a little bit ugly, but it will help us. So we have 2b squared equals 2g quantity squared. Do you guys see what I did? I just put the 2g in place of the a and squared that whole quantity.
I thought we were replacing b.
It's a that's equal to 2g. Yeah? Because it's a that we know is even. So tell me about this. What is 2g times 2g? Simplify that for me.
4g squared.
Yes, it is. And what can we do now to simplify this up a little bit? What could we get rid of to make fewer symbols?
The 4? No.
Better yet,
Square.
the 2, right? How do we get rid of that 2? This is being multiplied by 2, so what's the opposite of that?
Divide by 2.
Divide by the 2, divide by the 2, that cancels away. What is 4 divided by 2?
2.
2g squared. Now tell me about b squared. What's true about it?
It's even.
So b squared is even. And so, what about b?
It's even too.
b is even also. Now why is that a problem?
You can't have a fraction that is 2 even numbers that can be 2.
That's in lowest terms, right? We assumed it was in lowest terms, but we proved that both the numerator and the denominator, even if you thought you got it in lowest terms, both the numerator and the denominator would have to be divisible by 2, still. So it wasn't in lowest terms. So this is a contradiction. A and B can't both be even. So this is a contradiction. It means that our assumption that all of this was based on is that this can't be done in the first place. We supposed something, we followed it down, and we realized that the assumption couldn't be true. And so, that assumption just isn't so. That there is no fraction which is equal to the square root of 2.
Yeah.
Luca?
There's
Yeah?
the square root of 2 over 1.
But by fraction I mean I'm really saying rational number, which I mean is a and b are whole numbers, and it's in lowest terms. That's what I mean by rational number. There's no such thing for the square root of 2.
So there's got a guy killed.
It got a guy killed because they're like, oh no, the word of this can't get out. Pitch him overboard, they drowned him.
Wow.
Yeah.
Wow. What if he can swim?
Wait, what do you mean you swim? Oh, then
Well,
again,
it
this
was
is
a
like.
long way out and it was the ocean, so, you know,
Oh, yeah.
it wasn't good.
Sharks.
Drowned guy.
You know, everybody says sharks are like confusing for seals. So what? You're still getting, you're still.
So
getting
this is an example of an irrational number. Yeah.
It's not about like I know like a way to calculate like a square root, but I'm not sure if it 100% works.
Okay.
Like it said like on the thing my mom showed me on the computer. We looked up how to calculate square root.
Mm-hmm.
It's like they gave us an example called 27 and do the square root of 27.
Okay.
And what they said to do is like you divide 27 by your estimate.
Oh, and then it sort of converges on the square root of 2.
Yeah. And then I came up that it was like 27 divided by 5 would be 5.4.
Mm-hmm.
And then I myself thought about what if you did the square root of 4 and did 5.4 minus 0.2 and you came up with 5.2, which is close to the correct answer,
to the correct
which is 5.196 blah blah blah. Yeah.
Cool. All right, let's try this. So Cantor's diagonalization proof. A couple of you have Cantor's diagonal theorem. Oh, well, phi is going to have to wait. I know. Phi is cool, though, and we will get back to phi. The thing is, like, phi is the most irrational of all irrational numbers. So the
Sounds
square root of
irrational.
2 is irrational. What are some other irrational numbers besides the square root of 2? What else have we heard of?
Square root of 3.
Pi, the square root of 3. What else? Aiden?
Square root of pi.
E. You guys, did any of you who were last here with us last spring, we talked about E?
Yeah. Oh, I know what E is.
We went to E.
Isn't E like 2.828?
And then L.
It's 2.71828.
No, it's 2.828. We looked it on the computer.
182812828
Oh yeah,
and
you're
so on.
right. It's 2.71.
Yeah, it's
Internet has a lot of
2.7
lots.
Andrew Jackson. Or if you're in Soviet Union, 2.7 Tolstoy's birthday. E.
Go Tolstoy.
And then but it doesn't keep repeating after that. It's not rational. It does other stuff. Pi, what else? What other irrational numbers
The
are there?
square root of E.
Oh, phi.
The square root of pi.
I is not irrational.
Oh.
I is
How do
just
you get
not
pi?
even real.
What about what about
It's
tau?
imaginary.
Tau. Tau is like 2 pi, right?
Yeah.
Yeah, so tau is
Phi is
irrational.
irrational.
Pi is
What
irrational.
Is that
Square
something
root
with
of
an
tau.
dash in it? Is that the square
Wait, how
root?
do you get pi?
This is phi
Grace, how do you
or
get
phi,
that
depending
phi?
on whether you want to how you want to pronounce it.
Not even if it was
No, phi.
Phi.
Is not the square root of E. It's another kind of number.
It is another irrational number,
Yeah.
which we will come back to what that is another time. But we need to get to Cantor's diagonalization argument theorem. Yes,
the square root of pi.
square root of 5. Oh yes, of course.
Wait. By
Square root of
the
6.
theorem thing, do you mean infinity?
Huh?
Are we doing the infinities?
Yeah, we're doing infinity. Back to infinity.
0 to E is
So,
1.
here's the thing. Suppose that we wanted to think about all of the real numbers between 0 and 1. I'm going to draw sort of a sketch of this. Here's 0 on the number line. Here's 1. We want to talk about all of these numbers in here. Cantor's diagonalization theorem proves that there are more of these than there are counting numbers. Remember last time we were like, oh, I know the number of counting numbers is infinity. It's aleph null, right?
Yeah.
And then we were like, well, what about the even numbers? And they turned out to be aleph null. And we did the integers, the negatives and the positives, and 0, and it turned out to be aleph null. And we did the rationals, and it turned out to be aleph null. The irrationals are not aleph null. They are bigger. Here's a proof. Much, much, much bigger. So
Let's start with 0.1.
let's start with some. Here's what you're going to do. We're going to do another proof by contradiction.
Oh boy.
The proof by contradiction is, suppose you had a list. So suppose these are your pigeonholes. 1, 2, 3, 4, 5, 6, 7, 8, 9. Here are your pigeonholes. And remember, if you're going to have it, if you're going to say it's olive null,
Irrational pigeon.
you have to have each pigeon matched up with an olive null, right?
Yeah, but
However,
that's
you
not
might have had a
irrational
really super sneaky way to match these irrational pigeons up with these whole numbers. So what we're going to do is we're just going to suppose that you have a way to do it. So
Yeah, you let them fly into whatever hole they want.
yeah, well, but we say, and Grace says she looked, and it was done. All the pigeons had a pigeonhole. All the pigeonholes had a pigeon, and there were none left over. Grace said. So we're gonna prove to Grace that she was wrong. That she didn't see that. Sorry.
Dun, 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 dun.
So maybe the first one was this irrational number. 0.14159265358
We want to do that
9,
number.
7, 9, and it keeps going, but it
That's a
doesn't
big
repeat.
pigeon.
And maybe the other one is, can you give me the one for square root of 2 again?
No, it's
Oh,
it's
wait,
1
I can
4
tell
1
it.
5 9 2 6 5
4.
3 8 5 8 9 7 7 what?
What is it? 2, 1 point.
Wait,
Zero.
the square of
Excuse you.
4 2
Oh,
1
the
3
square-
5 6 2 3 7 3 0 9 5.
I'm sorry, Shlomo said it.
okay, I can
4,
say
what?
I
4
can
1
say
4 2.
Yes, 2,
135
1, 3, 5,
623
6, 2, 3,
7 3 0 9.
7, 3, 0, 9. Is that a
So
trustworthy
there's an
one?
untrustworthy 5.
Okay, good. And then, let's see, let's get another one. Oh, here's a good irrational number. 0.01. 0, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1,
What
0,
is this, you?
1, 1, 1, 1, 1, 0, 1, 1, 1, 1, 1,
1 1.
1, 0, and so on forth. This is irrational because it doesn't actually repeat. Even though there's a pattern to it. Here's another irrational one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6,
1 7 1 8
That's irrational.
Why are you
I
stopping?
get tired.
Let's do.
Juice.
Oh yeah. Hey, tell me which is right.
2
2, 4, 6, 8,
12
1, 0, 1, 2, 1, 4, 6, 1, 8, 1,
Oh,
2 0
2, 2, 2, 4. Oh, 2, 2.
Yes, 2 2
okay. What's another one?
I know one.
What?
Square root of 5
What is it?
is 2.236, and that's as far as I can remember.
Oh,
Hold
but-
on, hold on, hold
but I
on.
need more digits than that.
2, 3, 6, 0, 6.
Is it 0, 6, 7?
It's 2
Yeah. What is it? 2, 3, 6. What?
2 3 6 0 6
Yes.
We have awfully large
9
pigeons.
7 8.
Oh,
Wait,
that's
7 9
for
7
small
untrustworthy
pigeonholes.
8.
Untrustworthy 8. Well, that'll be good enough. Okay, that's enough. I'm good.
Oh, wait, one more.
Oh, one more.
I know
Agent.
Counting my threes.
What is it?
Counting my
Threes?
threes.
one more. No,
0.369 1 2 1 5 1 8 2 1 2 4 2 7
3 0.
0. That's kind of funny looking 3.
One more.
Da, da,
One
da,
more.
da.
Now we have to
Oh,
count.
you got one more, Grace?
We counted by evens. Now we have to count by odds.
Oh, you're right.
1
1 3 5 7 9 1 1 1 3 1 5 1 7 1 9. Okay, that's enough. All right. Now wait. Here's Cantor's diagonalization argument.
So you have all the
Grace said she looked, and every pigeonhole had a pigeon.
You want me to stop before they run?
But I can find another pigeon in there.
And they kept going all the way.
All the pigeons
Grace
haven't-
said she found a way to do it.
Uh-oh.
We're going to prove to Grace that she's wrong.
I don't even believe
Dun,
it.
dun,
I know, that's why it's not fair.
I know.
But we're going to find a pigeon that isn't in Grace's system.
I found a pigeon.
Here's how it is.
It's 1.
We're gonna look at the
0,
first-
4, 1,
We're going to look at the first digit. What is it?
1.
1.
One.
The second
You
pigeon
change
is
it to
second.
Wait,
0.
pick a number that is not 1.
Ooh,
2.
5.
5.
5,000.
Now we're going to look at the second number. We're going to look at the second digit. It's a 1. Pick a number that is not 1.
5.
3.
3. Let's go 3.
Yeah.
We looked at the third digit. It is a 0. Someone give me a number that is not 0.
100.
1.
13.
1.
Oh yeah.
We look at the fourth one. 1, 2, 3, 4. We pick a number which is not 4.
5.
3.
5. That's the first one I heard. 1, 2, 3, 4, 5. We look at the fifth.
6.
Okay, 6 instead of a 1. We go over here. 1, 2, 3, 4, 5, 6,
7. 8.
10.
8.
10.
I said
10
7.
isn't a digit.
I said 7.
Oh, wait.
8. I said
Hey,
7.
But
hey.
I got
seven is,
almost
um,
over
is the one we had. It can't be 7.
8.
9.
8.
9. 1, 2, 3, 4, 5, 6, 7. Not a 5.
6.
2, I heard. Okay, finally. 1, 2, 3, 4, 5, 6, 7, 8.
3.
8.
3.
Yeah.
Okay, we keep going like this. We go all the way down for all the pigeonholes and all the pigeons, and we make sure that each pigeon number, digit, is different than that pigeonhole. This pigeon will not be on Grace's list.
Pigeon.
It's a bit of a confused pigeon.
This pigeon
Pigeons are
is
weird.
different from every other pigeon on her list in at least one place. So that pigeon can't be on her
Because
list.
all my pigeons are black and that one's white.
So,
That's wrong.
so this proves that actually the cardinality of the set of real numbers is greater than Aleph null.
Wow.
And there's actually a question, and this is called the continuum hypothesis. This is something that's,
Sounds continuous.
it's either unknown or it's something you have to assume, depending on who you are in mathematics. But there's something called the continuum hypothesis that allows you to presume that actually the infinity of real numbers is the next biggest after the infinity of naturals. But some other people worry that maybe there's a way to have infinities that are between the size of the naturals, the counting numbers, and the continuum of real numbers.
But how do you get more infinite? You can't get more infinite. It's
Oh, you can get, this is
you can get-
more infinite.
That's more infinite than Aleph null.
This is more infinite than Aleph null. There are more of these. In fact, it's even worse. If you throw a dart at the real number line between 0 and 1,
Cool.
you are 100% likely not to find a rational. You will not hit a fraction, not a rational.
Wow.
100% of the time you will hit an irrational.
Wow. So that's all the time.
Because there are so many more irrationals. And this is what's crazy about that. Here's a half, right?
Yeah.
Yeah.
Here's a fourth. Is there a number in between a half and a fourth?
Yes,
Yeah.
there's a lot of numbers.
Yeah? For example, I could say this is really 4/8 and this is really like 2/8, right? So one
there's
number in
3/8.
between here is 3/8.
And then
Is there one between 3/8 and 4/8?
yes, some odd 16ths.
Right? So it's going to be like this, or 3.5/8, right? Something like that. It's going to be some 16.
So
you
that'd
put
be
it as a
like
rational number.
7/16ths.
7/16. That sounds good because this would be 8/16. That's 6/16. So there's another one. And in fact, between any two rational numbers, there is always another rational number.
Yep.
They are dense. And yet, if you throw a dart at the number line, you will not hit one of
As
them.
long as the tip of the dart
You will
is
hit,
equal to the size of a point.
well, yes.
And then
You will
We're
hit
assuming
an
that.
irrational number.
what if
Guaranteed. And here's why. Think about how hard it is to do. Suppose you wanted to hit a half
with a dart.
with a dart.
With the BB.
You would have to hit first
yeah.
a point in the tenths place. You would have to hit a 0.5, right?
Yeah.
And what would you have to hit in the hundredths place for this to be a perfect half?
0.
And what would you have to hit here?
0.
And what would you have to hit here?
0.
And what would you have to hit here?
0.
And what are the odds of being able to do that forever? 0%. You will not hit it. Cannot happen. So you can never randomly hit a rational number. You will hit an irrational. 100%.
What
Yeah.
about?
Wait, a rational number that
No
you
one
could do
either.
with half is like you could say you start with 1. You add like this is a irrational number bigger than 1. If you like say 1 plus half of 1 is 1.5, and you keep on doing it plus 1/4, then you will. If you keep on going on forever, you'll get a irrational number. If you keep on going forever, that's it.
If you keep going forever with 1 plus a half plus a fourth plus an eighth like that,
Yeah, you will
Plus
get
a
it.
16.
let's
Yeah.
hold that thought and think about what would happen if we did that the next
37.
time.
This
Plus
is
a
not,
64.
I don't know,
Plus
this
a
is just
You're actually
128.
over time.
Plus a 200.
I'm not sure if I.
this is just hard to
512.
grasp.
Yeah,
It's just
go ahead.
Plus a
I'm not sure what I think
1024,
about the
plus a
different sizes of
20,
infinity.
2048,
Okay,
Because
plus a
since
4096.
it's almost.
since the numbers of our pigeonholes keep going,
Yes,
they don't stop,
yes,
and the other ones also keep going.
yes.
I'm not sure.
All right.
Because unless they stop, one can't be bigger than the other one.
Unless they stop. Oh, I see what you're saying.
Yeah.
The idea is that if you can find a way to match the two, which like last week
Yeah.
we were trying to match the even numbers up with the whole numbers. We found a way to do that. We found a way to match the integers with the whole numbers.
Yeah.
And what we were doing here is we were assuming we found a way to match them up, and then found a proof that we could find another one that wasn't on the list. That no matter what arrangement you thought you had that would match them up, we can destroy it.
Wow.
You can make a different arrangement
You
though.
can make a different pigeon. Oh, but sure.
So
but
you
once
can
you've
keep
said,
making more arrangements.
but you have to
but
stop.
you'll never get the right arrangement.
Right, but that's the thing here. For the pigeonhole principle to work, you have to have an arrangement that matches them. That's done.
Mm-hmm.
And once it's done, if we can
Yeah.
destroy it, it's destroyed. But I see what you're saying. Like you're like, well, if you're allowed to go back and forth, sure, you
Yeah.
could squeeze any
Yeah,
other pigeon
yeah,
on
like-
the list.
Yeah, like what if you buy another set of pigeons after they're destroyed?
Or you just put
want to buy
in new